Hi everyone, I'm Shuanger Ma from Bar-Ilan University. The topic of my talk today is loss of resonances for noisy quantum recurrence with restarts. My motivation is following. The noise limits the practical implementation of quantum computers, and our group has investigated how the quantum recurrence work. Without noise. However, when we do experiments on the quantum computer, we find that the noise in the quantum computer heavily influence the results. So our goal is to investigate how noise affects the statistics of quantum heating times. In noiseless scenarios, heating times can exhibit exponential speedups compared to classical systems. And all these questions are related to quantum computing with mid-circuit measurements, which are inherently sensitive to noise. My talk will be divided into two parts. The first part is model setup, and the second part, I will talk about how noise influence the system with an example of flip noise. Firstly, a bit flip in a single qubit. Then I will make an extension to a three-level system. And finally, I will make a conclusion to this topic. And the main message I want to convey is that noise has a greater impact on systems with degeneracies than on non-degenerate systems. And resonance arises due to degeneracy-induced dark states, and noise helps remove the dark states, enabling full exploration of the Hilbert space. The model I use is the following. A quantum particle on a graph evolves via a time-independent Hermitian Hamiltonian edge, and the Hamiltonian is constructed using a tight binding model. The quantum recurrence is that the initial state and the target state are the same. So here the figure shows the stroboscopic measurement in this system. The system encounters first a unitary evolution, and then Q represents a non-successful measurement. If we do not detect the target state, and we will continue to this process until we finally got a successful detection at the target state. So we can write the amplitude of the wave function of the successful detection at the nth measurement. And first detection probability is the absolute square of the amplitude. And now we study the impact of post-unitary noise. It is after the unitary evolution and before the measurement. And we use the density matrix and cross operators to represent the noise. So we can write the average detection probability, the average Fn. However, the problem of this formalism is that this operator acts on both sides of the density matrix. So it's hard to write a general formula of the average detection probability. So we use the vectorization formalism. The density matrix can be vectorized into a vector, and the operator action becomes the tensor product of the original operator and its complex conjugate. So we can write the first detection probability in the form of matrix multiplication. We also use the generating function to analyze these problems. Useful quantities, such defined as the detection probability and the mean detection time, can be expressed in the form of the generating function. Now, I'll talk about the bit flip in a single qubit. First, there are two sides in one qubit, and that's 0 and 1. The initial state, we set it to be the ket 0, and the target state is also this. The Hamiltonian is constructed using the tight binding model, so in the two-level system, it's negative poly X matrix. And the measurement and the noise operators, the flipping probabilities between the two states is we set it to be P. So the noise operators are poly X matrix and I with probabilities P and 1 minus P. So after some computation, we got the detection probability at the nth measurement. Using these detection probabilities, we can find the mean detection time. When there's no noise in the system, we see that there are resonances. However, when the system is with noise, the mean detection time would be constantly at 2. And we are also interested in the restart strategy in this system. A restart strategy reinitiates the process after a TR unsuccessful detection steps. TR is also called the restarted time. And the conditional mean is defined in equation 6. We are interested in the disappearance of the resonance, so we analyze the problem in the low noise and near resonance regime. And we find the formula of the conditional mean is written here. And we also plot the curve of these conditional mean. And we find that when TR is large enough, the conditional mean approach to 2. So, and the resonance disappears. And now I will make an extension to the 3-level system. There are 3 sites in this system. And similarly, we set the initial state to be cat 0. And the target state is also cat 0. So it's a recurrence problem. And the Hamiltonian is constructed also use the tight binding model. The flipping probability between the nearest sites is P. And because it is noise, and so the flipping probability is usually very low. So the possibilities that 2 flipping happen simultaneously will be neglected. So the noise operators can be constructed, represented like this. And we used the generating function to analyze these problems and got this statistics. We see that in equation 7, the problem is that it's hard to do the matrix multiplication of the survival operator S. So we use a spectral decomposition of these for this system. And it has 9 eigenvalues in the 3-level system, and the absolute value of the eigenvalue is usually less than 1. And we also write the initial density matrix as a linear combination of the eigenvectors of the survival operator. So we can rewrite the generating function in equation 8. And using the symbolic program in Mathematica, we found that in the noisy system, or 3-level system, the mean detection time is constantly at 3. And comparing it with the no noise system, we find that in the mean detection time when there's no noise in the system is 2. And there are also resonances, and the jumps to 1. However, with noise, the mean detection time in the system is constantly at 3, and even not 2. It's the dimension of the Hilbert space. And we also investigate the conditional mean of the of this system, and we found the result is in equation 9. And we also and this is only valid when tau is far away from resonance. So we plot the result and the simulation result into this figure, and we see that Monte Carlo simulation theory and numerical results fits well. And also when TR is very large, the conditional mean goes to 3. And we also, because this result is only valid when tau is far away from resonance. We are also interested in in the scenario that it is close resonance, how the resonance disappears. So the result is written here, and it is similar to the two-level system. The result is similar, and we show the figure of the combined results. And from the result, we can see that when TR is large enough, the conditional mean approach to 3, and that the resonance is lost. And now I want to say that our key observation is that flip noise reveals all dark states, and so it enables full exploration of the system. So the mean detection time with unlimited attempts, or TR is large enough, approach to the dimension of the Hilbert space. And I also show the numerical test for the 6-side ring to see if my conclusion is more or less correct or not. From the definition of the conditional mean, we see that when TR is very large enough, the conditional mean converge to the mean detection time. So because it's a numerical test, and I cannot really calculate the mean detection time when TR is infinite. So I use the conditional mean to represent the mean detection time. And without noise, the mean detection time shows resonances, and maximum value is 4. However, with noise, the conditional mean goes to 6, confirming the Hilbert space dimension. And that's the end of my talk. Thanks for listening.